Swayam Prabha. Digital India. Educated India.
Welcome to the Pharmaceutical Organic Chemistry 3 paper. So now we are going to study about the first unit. This is Stereoisomerism part 1. In the first lecture we will be studying about optical activity and stereoisomers. I am Dr. Balaji, currently working as Associate Professor in the School of Biotechnology at Jawaharlal Nehru University. This project is sponsored by DTH Swayamprabha, New Delhi, MHRD. The topics that will be covered in this session include details of what are stereoisomers, what is optical activity, and we will also be studying about RS nomenclature. We will be studying elaborately about what are enantiomers, diastereomers, and meso compounds. Welcome to the next session on pharmaceutical chemistry, paper 4. We will be starting our studies using optical activity and stereoisomers. In the glossary, we have given a few terms like stereoisomers, optical activity, plane polarized light, and these are all the terms we will be encountering in this particular session. We will start with a very basic fundamental thing, that is from isomers. So what are isomers? Isomers are generally divided into broad two categories. The first one is constitutional isomer, which includes structural and positional isomers. They have different bonding arrangements of their atom. In other words, the connectivity only will be different in these kind of constitutional isomers. The second one is stereoisomers. So here the molecules will have identical connectivity but different spatial arrangements of their constituent atoms that cannot be interconverted by bond rotation. So this is the most important thing we have to remember. In the case of stereoisomers, the bond rotation does not give constituent isomers. So broadly we have structural isomers or the constitutional isomers, and the second one is the stereoisomer or the spatial isomers. So the structural isomers can be further classified into chain isomers, positional isomers, and functional isomers. Stereoisomers are generally classified into geometrical isomers and optical isomers. So when we talk about configurational isomers, they are actually geometric isomers and optical isomers. And the second major class is conformational isomers. So what is the difference between configurational isomers and conformational isomers? Basically, the conformational isomers are formed by the rotation of bonds, whereas in the case of configurational isomers, the new isomer or the other isomer is formed by the breakage and joining of the bonds. So simple rotation does not give configurational isomers, but simple rotation gives conformational isomers. And in the case of optical isomers, we have enantiomers and diastereomers. In this particular session, we will be studying about these enantiomers and diastereomers. And in the coming sessions, we will be studying about the geometric isomer, that is cistrons or EZ isomers. Let us look at the historical development. Before we delve into studying about enantiomers and diastereomers, we used the word optical isomers. So what do you mean by optical activity? So that is what we will start from the beginning. So in 1815, Jean-Baptiste Biot discovered that some natural substances like glucose, nicotine, and sucrose rotated the plane polarized light, and other compounds did not rotate the plane polarized light. So this is the first observation by John Bay. So he first observed that some compounds like glucose, nicotine, sucrose, etc. rotated a plane polarized light. Now we will also see about what is called this plane polarized light very soon. And later in 1848, Louis Pasteur recrystallized sodium ammonium tartrate. So the tartaric acid is given here. This was converted into sodium ammonium tartrate salt. So this compound did not show any optical activity. That means it did not rotate the plane polarized light. But Louis Pasteur did not stop there. So what he did was he found out the crystals were of two types as shown here. One is having like a left-handed arrangement, another one is having a right-handed arrangement. So like that he identified these two types of crystals using microscope. Then what he did was the major breakthrough in organic chemistry. So he started physically separating them using a tweezer. So he first painstakingly identified each crystal and he separated the left-handed crystal separately and the right-handed crystal separately, and he just used one of the crystalline substance and he studied the optical activity of that particular substance, and he found out that both the crystals were individually optically active. And another important thing what he identified was they rotated the plane polarized light exactly in the opposite directions with the same magnitude. But when he mixed 1:1 ratio of the two crystals, they were optically inactive. So these are all the major developments by Louis Pasteur in the optical activity field. So fast forward to 1874, Van Hoff and Lebel proposed that tetravalent carbon atoms are tetrahedral, because we know the valency of carbon, which is 4, but whether it is a planar one or a tetrahedral one was a big controversy going on back then. So if we look at the square planar case where the carbon and 4 other groups are arranged in a plane, we will be having plane of symmetry. If a molecule has plane of symmetry, then it cannot rotate plane polarized light. So that means this structure is not the right tetravalent structure for the carbon. So he proposed the tetrahedral structure for the tetravalent carbon. So here there is no elements of symmetry, and based on this tetrahedral arrangement we can explain optical activity. So this is how the optical activity historically developed. Let us look at the definition of what is optical activity. A sample or a material, that is a molecule, will be able to rotate the plane polarized light is said to be having optical activity. So this is the basic fundamental thing. You take any substance or a molecule, you dissolve in a solvent and pass the plane polarized light through the substance, and if it rotates the plane polarized light, then we say the molecule or the compound is optically active. And the other two terms which we will be encountering later are the enantiomers and diastereomers. They both show optical activity or optical rotation. An isomer having a rotation in the clockwise direction is called a dextrorotatory or plus isomer, and the one causing a opposite sense, that is the anti-clockwise rotation of the plane polarized light, is called a levorotatory or a negative isomer. And one more thing we have to remember is when there are n stereo centers, that is stereogenic centers in the compound, leads to 2 to the power n of stereoisomers. So these are all the some basic fundamental things about optical activity. Now the question comes to, what do you mean by plane polarized light? So the light is basically having multichromatic, that means it has various wavelengths of electromagnetic wave radiations put together forms a light. And when this light is passing through a monochromator, so what we have? We have a multichromatic light, that means it has various wavelength, and when a monochromator is kept in the path of the light, what it does is it filters out all the polychromatic light and it only gives out monochromatic light. But this monochromatic light is again unpolarized. In other words, they can go in all directions. So when we say plane polarized light, that means this is not a plane polarized light. This is only a monochromatic light. That means it is having a single wavelength. And when this monochromatic light passes through a polarizer, so what the polarizer does is it only allows a plane polarized light. That means the electrical field of the light is aligned in one particular direction. And when it is aligned in one particular direction, we call that as a plane polarized light. And the next question we have in our mind is, why do we need to use monochromatic plane polarized light? Why not use normal light? Because if we use a normal light has two major components as we mentioned. It is the polychromatic one. That means there will be various wavelengths of light in that particular electromagnetic radiation. And the second one is like they will be going in all directions. So that means if we pass a light having polychromatic wavelength and dispersed in all directions, we may not be having any ability to check the light which is coming out of the solution. So to have a very clear understanding of what is the light coming out, whether it is rotated to the right or to the left, we do need to know, we do need to use monochromatic plane polarized light. So let me explain with a simple analogy model. So there is multiple bags inside a room, and in that room this is equivalent to polychromatic light. That means there are multiple colors bag are there in a room, and there are a lot of people inside the room, and there are various exit in that room also. So our job is basically to find out how many people, if the people are allowed to take two bags per person, and when they are coming out, we have to measure how many people came out and how many bags they have taken out. So this is going to be a big challenge because we have one, two, three exits are there. So that means we have to monitor all the three exits. And another major problem is they can bring any color back. Say for example, this person brings two different colors, green and orange one. This person brings maroon and an orange one. So like that, every person brings a different color. So that means it will be very difficult for us to count them in a very quick way, and this is leading to a chaos. So to avoid that, how we can overcome this problem is very simple. I know you got the idea. So the first thing what we have to do is we have to close all the doors except one. So if all the doors are closed, then there is only one exit for the people to come out. Okay. Then the second one, they should be permitted to bring only one single color bags. They should not be allowed to take any color. So how do we compare this with the monochromatic plane polarized light? So you are shutting down all the doors is equivalent to making it plane polarized. That means there is only one exit point for everyone. And instead of allowing them to carry any colored bag, we allow them only to carry a red color bag. So that means this is a monochromatic one. So that way we can easily control how much of the bags are coming out of that room. We can easily control. The second most important thing what we can do is basically doing a bag calculation. If there are more number of red bags are being taken by the people, then we can actually do a bag calculation to find out how many bags were there in that room. So that is also possible to back calculate, because more number of people bring more number of red bags means this is directly proportional. In other words, the sample concentration directly affects the magnitude of the plane polarized light which is coming out of the solution. So let us look at what is optical rotation. Optical rotation, as we mentioned, has a dextro-rotatory or levo-rotatory. That means when a plane polarized light is rotated in the clockwise direction, it is called, and when viewed through a polarimeter, we say plus or D. And of course, you shouldn't get confused with the capital D. So here it is mentioned as a small d, and we will see the difference between what is a capital D and a small d. The small d is always referred to optical rotation, that is dextro-rotatory, and the capital D and capital L are generally used for Fisher notation. We will be studying about this DL notation soon. So in the case of levo-rotatory, when the plane polarized light is rotated in the counterclockwise direction, we say this is a negative or a L, small l. So this is how we actually correlate optical rotation. And as we mentioned earlier, how much the angle rotated is specific for a particular substance, and the intensity of the light which is coming out is directly proportional to the concentration of the solution. So next term is a specific rotation. So if we say simply optical rotation of a compound is X, then different people using different colored wavelength and different people using different solvents and different people using different wavelength, all this will give different readings when we use the polarimeter. So we may not have an accurate value of reporting what is the optical rotation of a particular substance, because optical rotation basically depends on the concentration of the solution, the wavelength of the light used. So in order to have a very specific value, we use a term called specific rotation, and in this specific rotation what we generally do is the angle of rotation of the plane polarized light by a 1 gram per ml of a sample in a 1 decimeter tube using a lambda is, that is a particular wavelength. Here we say D is a sodium lamp and its lambda is equal to 589 nanometer. So we have various parameters which are fixed. The first one is weight of the substance is fixed, that is 1 gram, and the length of the tube is also fixed, which is 1 dm, and we are also taking this in a 1 milliliter of the sample. So that means the sample volume is also fixed, and alpha D, which is the sodium lamp's wavelength, is also fixed. So that means any person reporting this value can be easily reproduced by other people. So that is why we generally use specific rotation and we do not use optical rotation. So the equation given is alpha D. T here, the small t here is the temperature, the capital T is the wavelength that is used in the polarimeter, and alpha is the observed rotation. So this alpha is the one which keeps changing, whereas alpha D at a particular temperature remains constant, because we are using a constant, that is the length of the tube is 1 decimeter and the concentration is also gram per cc or gram per ml. This is also a fixed value. So that means the optical rotation whatever we obtained is can be reported very easily in terms of specific rotation. So here we had given the values for alanine, which is plus 8.5 degree, and for minus lactic acid it is minus 3.8. So here we mentioned 25. 25 is the degree temperature at which the measurement was done, and D is the sodium lamp D line, which is having a lambda of 589 nanometer. Now let us look at what are enantiomers. Enantiomers is a pair of stereoisomers that are related as non-superimposable mirror images. So if we take a carbon with the 4 different groups surrounding the carbon, then we say this compound can be optically active, because one of the criteria for optical activity is the 4 atoms of the group attached to the central carbon atom has to be different. So here we have X, Y, Z W. So we have 4 different groups. Here also, if we look at the right hand side one, this is exactly the mirror image of the left hand side one. So if we try to superimpose these two things, they are non-superimposable, but these are mirror images. So any non-superimposable mirror images are called enantiomers. Here we have some examples of enantiomers. So we have a simple compound, 1 carbon, 2 carbon, OH. So that means this is nothing but ethanol. We have HR and HS. That means if this hydrogen is replaced by a deuterium, then what type of isomer we are going to get, that is mentioned here. If this is replaced as shown here, we are going to get a R isomer, and if this hydrogen is replaced by deuterium, we get a S isomer. We will soon study about what is this R and S nomenclature or the notation that is being used for representing chiral carbon. Before we go into that, I'll just give a brief information about the color coding which is used in chemistry. So we generally use the Cpk Color Scheme. So this is developed by Corey and Pauling, and they have used a space filling model in 1952, and this was later improved by because in this model they have actually used the X-ray diffraction studies of protein. They wanted to represent the structure of protein using molecular models, so they used the CP model in the beginning, and their end objective was to rule out sterically improbable conformation for protein structures. So their main focus was to identify how we can represent the molecules in physical terms. So that is why they developed this CPK coloring model. So they have generally in the beginning they used white for hydrogen, red for oxygen, purple for phosphorus, blue for nitrogen. Of course, I try to keep the similar colors for the representations which will be used in this particular session, and later on in this particular paper we will be trying to use the similar colors represented by the CPK coloring scheme. And this is the original paper reported by Robert Corey and Linus Pauling. So here they had shown the space filling model for the protein structure. Here I don't know whether you can very carefully see, here the hydrogen is represented, hydrogen. So wherever we see the white color, these are generally representing hydrogen atoms. So this is the protein structures. They want to see the exact structure of the protein, and they try to compare it with the X-ray diffraction studies so as to find out which particular conformations are not possible. So this is how they started molecular model representation. Later on, Colton patented an improved method, so that is why now it is called the CPK model. And many softwares, basically Jmol, Rasmol, Avogadro, Pymol, etc., have their own color schemes. So here I had given one such example of a color scheme which is generally used. So hydrogen is white, carbon is ash color or little bit black, oxygen is red, nitrogen is blue, and chlorine is green. So these are some of the standard colors which are used, and you can also see that in many of our representations we will be using this particular color. Now let us look at what is R and S configuration we have just mentioned. So we have to identify whether this compound and this compound are the same or different, because whenever we write a tetrahedral carbon, people can very well represent all the 4 atoms at their own choice, and if a person A represents in one form and the person B represents in an entirely different form, whether they are the same compound or they are different compounds, we do need to know. So to compare these two things, people have started using RS nomenclature. So here we have certain rules which we have to follow. This is also called Kohn-Ingold-Verlag system or CIP rules. So in this particular case, we are the step 1 is assign sequence priority to the groups or atoms using a sequence rule. So in the sequence rule, what we generally use is higher atomic number compounds get the highest priority in numbering. So following that, if we have to represent this one, The oxygen is having higher atomic number compared to nitrogen, which is having higher atomic number compared to carbon, which is having higher atomic number compared to hydrogen. So the central carbon is the main part around which four different groups are attached, and we have to give priority for each atoms or groups which is attached to the stereogenic center or the central carbon atom under consideration. So in the second step, what we have to do is we have to visualize the molecule by moving the lowest priority group away from the viewer. So here hydrogen is the lowest priority group, so it is already kept away from the viewer. And step 3, observe the arrangement of groups. If they are clockwise, then it is R. If it is anti-clockwise, it is S. We will see now what this actually refers to. So as I mentioned, OH is having the highest atomic number, so the priority is given to number 1 to oxygen. The second one is nitrogen, which is getting the priority number 2, and carbon, which is having a lowest atomic number between all the three, is given the priority number 3. So oxygen is 1, nitrogen is 2, carbon is 3. So 1, 2, 3 is the way in which we have represented, and this 1, 2, 3 is in the clockwise direction. So this type of arrangement is called R arrangement, or in other words R configuration. So that is how it is represented as R. And if we take the other one, 1, 2, 3, that is oxygen, nitrogen, carbon, priority is in the counterclockwise or in the anti-clockwise direction. So this is represented as S configuration. So this is how we can actually represent R and S for any chiral center, and based on that we can actually give the configuration for all the stereogenic centers in the molecule. Let us look at the three-dimensional representation of the molecule which we have seen. So here I'll just rotate so that you can actually see what are all the oxygen is written here as O, hydrogen is written here, nitrogen is here, and carbon is here. So these balls, white balls, are basically hydrogen atoms, and as we mentioned earlier also in the Cpk model, oxygen is having a red color, nitrogen is having a blue color, carbon is having an ash color, hydrogen is having a white color. So this is how we can actually represent the molecule. Now for our convenience, I will just remove some of the hydrogen atoms on carbon, nitrogen and oxygen, so that our view becomes much easier. I have removed all the hydrogen atoms so that we can have a better view of the molecule. So as we mentioned here, what we have is the carbon is in the back, nitrogen is on the left, hydrogen is on the right. So we were actually trying to make the replacement of hydrogen and carbon so that one moves in the front and one moves in the back. So if we have to do that, what is the best way to do is, if I rotate the molecule like this, now what comes in the front is carbon from the back comes to the front, nitrogen which was earlier here moved to the right, and the hydrogen which was here actually moved to the back. So this is how the entire molecule actually rotates. Now you can actually see how the whole molecule can be rotated. So if I rotate like this, now what happens? The hydrogen comes to the front, carbon is on the right, nitrogen goes to the back. And if I rotate one more time 120 degree, the hydrogen is in the front, nitrogen is also in the front, because this is how we write the projection formula, and carbon is at the back. So sometimes when we represent the oxygen, the carbon and the hydrogen is on the plane, so we can write them with the normal single line. Then this nitrogen is projecting towards the observer, so that means this has to be written with the wedge bond, and this carbon is behind the plane, so it should be written like a broken bond. So this is how we generally represent the three-dimensional structure of a molecule in a two-dimensional paper. So here once again I rotate for your convenience. Otherwise what you can also do is, this hydrogen is pointing towards the observer. This nitrogen is also pointing towards the observer. This carbon is behind the plane, and oxygen and carbon are in the plane of the paper. So in other words, if we have to represent this one, how we can represent is oxygen and the carbon in the plane we can write. This hydrogen and this nitrogen will be projecting towards the observer, and the carbon is behind the observer. So two wedge bonds and one broken bond and one straight bond. So this is also another way of representing the molecules. I will actually put the side by side. I will be writing the two-dimensional structure. This is a three-dimensional structure. So if you compare two-dimensional and three-dimensional structure, you can easily visualize and understand the stereochemistry of the compounds very easily. So always remember, whenever we have to move an atom or a group, what we have to do is we have to rotate the bond, and we are not supposed to break the bond and join it. So if I rotate this, the hydrogen now goes to the back, and the nitrogen comes to the right, carbon comes to the left. So in the priority wise, if I have to write, oxygen is having the highest priority, followed by nitrogen, followed by carbon. So this is 1, 2, 3. So this is in the clockwise direction. So this is a Are isomer. So the CIP rule, or the Con in gold prolog sequence rule, states that what we need to do is rank the substituents, that is the groups or atoms which are attached to the chiral center or the stereogenic center, which is directly attached. So this is what is the most important thing. We have to look at the direct attachment of the groups in the order of decreasing atomic number of the first bound atom. In other words, in the previous one, oxygen is having the highest priority, so it is given the number 1, followed by nitrogen number 2, followed by carbon number 3. And if we are using isotopes, say for example hydrogen isotopes H1, H2 and H3, in that case what we have to follow is any higher isotopes takes precedence over the lower isotope. So in other words, H3 gets the priority, that means this will become number 1, H2 will be number 2 and H1 will be number 3. So this is how when we are using isotopes we have to follow. And the lone pair counts as the lowest priority of substituent. So this is the least priority substituent. If hydrogen and electrons are there, the electron gets the lowest priority. And if we are unable to differentiate in the first atom, then we have to move on to the next atom. So that is, consider atoms at increasing distance until a difference is found. So we have to keep on moving until we identify there is a first difference. Based on that we will have to give the numbering. And for the purpose of ranking, what we say, a multiple bonded atoms is considered equivalent to the same multiple of single bonded atoms and has higher priority than the corresponding single bonded substituent. In other words, if we have to represent a carbonyl group, that is C double bond O, what we have to do is, instead of making it a C double bond O, we have to make two single bond O, that means C dash O and C dash O, and based on that we have to give the priority. Let us look at how to find out the absolute configuration of S-alanine. So here we have shown alanine in this structure. So here what we need to do, the rank the substituents on the stereogenic center in the order of decreasing priority using sequence rule. So according to the sequence rule, nitrogen is the first attachment, carbon, we have two carbons. If you look at carboxylic acid and the methyl group, we have two carbons, which is the first attachment. In the carboxylic acid, if we go to the, as we mentioned earlier, if there is a match in the first one, we have to go to the second attachment. So that means from the carbon we have two oxygens, that is carboxylic acid's double bond oxygen and OH is present on this carbon. Here we have all the three hydrogen. So that means between oxygen and hydrogen, which is the second attachment, oxygen gets the priority followed by the hydrogens. So in other words, carboxylic acid gets the priority number 2 and the methyl group gets the priority number 3, and finally hydrogen gets the least priority, which is number 4. So we have to assign the configuration for this particular compound. Now, what is the second rule says? We have to view the stereogenic center with lowest priority substituent pointing away. So this is the lowest priority substituent, but as a wedged edge, it is actually pointing towards the observer, and this broken one, that is the methyl group, is actually pointing away from the observer. So now we have to move this hydrogen to the back. So how do we move that hydrogen to the back? Can we simply replace this hydrogen and the methyl group, or we have to actually rotate this molecule? We will now see how it has to be done. So the first one, what we have done is the NH2 group is on the left hand side, it is again on the left hand side, the carboxylic acid is at the top, carboxylic acid is at the top. Now hydrogen is pointing towards the observer, that I simply exchanged, moved to the back side. So is this the right way of representing this molecule? Unfortunately, this is wrong, because as we mentioned, whenever we talk about configuration, we are not supposed to break any bonds. Only rotation of the bonds are allowed. So if we have to move this hydrogen from the front to the back, if we have to move, then what we literally have to do is we have to break this bond, then we have to break this bond, then reattach them to get this one. So whenever we break the bond, that actually is changing the configuration. So we cannot do that operation. So that is why this operation is a wrong operation. So how we can do that? Another way to do that is we have to move all the three groups simultaneously. So that means this one has to move towards the right hand side, if I say. So from here it had come to the front. Simultaneously the hydrogen has to go back. So hydrogen went back, and the methyl group which was behind comes to the place of NH2. So that is how it comes here. So this is how we have to rotate the entire bonds and not break the bonds and attach the bonds. So this is one thing you have to always remember whenever we are going to assign the configuration. You have to make sure that rotate the lowest priority group away from you. I will show a demonstration for this one. Here is the representation of alanine molecule. We have a carboxylic acid group as the top, and the amino group on the left hand side, hydrogen on the right hand side, and the methyl group in the behind. For simplicity, I will now remove all the hydrogens which are not required. As we mentioned earlier, in this particular case, we will be looking at the priority of the groups. So nitrogen is the highest atomic number in this particular alanine molecule. So this will get the priority number 1. And then we have two carbons, the carbon with the 2 oxygens and the carbon with the 3 hydrogens. So we need to find out which one will get the priority. As I mentioned earlier here, each double bond will be considered as 2 single bonds, and there is also another single bond. So this carbon has 3 oxygen as the second attachment. This carbon, if you look at this, has hydrogens. So that means between oxygen and hydrogens, the oxygen gets the highest priority. So this carboxylic acid unit gets the second priority, and the methyl group gets the third priority. So let me remove some of the hydrogen atoms for simple viewing. I just remove the hydrogen from the oxygen, the hydroxyl OH, the hydrogen I have removed, and from the back methyl group I will remove all the 3 hydrogens for easy viewing, and here now I am removing the nitrogen's hydrogens. So this molecule now becomes much easier for us to view. So in this particular case, the hydrogen is pointing towards the observer. As we mentioned here, the hydrogen is pointing towards the observer, and the carbon is behind. The methyl carbon is behind, and the carboxylic acid is in the plane. Amino group is also pointing towards the observer. So in this particular case, as we have to give the RS configuration for this one, since the hydrogen is in the front, we have to rotate it in such a way that the hydrogen goes to the back. So when we rotate the molecule, now hydrogen went back and the nitrogen is in the right hand side, the carboxylic acid is in the top and the methyl group is on the left. So according to this one, if we assign the priority, the nitrogen is the highest priority number 1, this is the second one, this is the third one. So this is in the counterclockwise direction, or it is in the, this is called the S isomer now. If it is clockwise, we call that as a rectus or R isomer. If it is in the counterclockwise, we call that as a sinister or S isomer. So that means this alanine molecule is a S isomer. So two-dimensional representation of the same alanine is given here. So as we mentioned, we had seen in the three-dimensional one, here the hydrogen is behind. The NH2 group is in the front and the methyl group is on the left, carboxylic acid is on the plane. So this, since 1, 2, 3 are in the counterclockwise direction, so this is called the anticlockwise or the counterclockwise. So this is the S alanine. That's how we can confirm how to assign R and S configuration. We will look at a few more examples of enantiomers. Here we have pentane diol. Two isomers are given here. So these two are basically enantiomers. So if you look at the molecule and this one, these two are exact mirror image of each other. So here the central carbon with oxygen is represented here as shown here. So this carbon's Norman RS notation is S configuration, and for this one, this is S again. That means the OH is pointing towards the observer. As you can see, the oxygen is pointing towards you. The same way here also it is pointing towards you. So here again this is a R configuration. So if you look at here, it is R and it is S. So how does pointing towards the observer keeps changing? That is basically based on, if we assume this as our stereogenic center to which we are going to assign. So we have a methyl group here, that is what is given here, CH3 group here, because for simplicity the hydrogens are not shown here. So this is a methyl group, there is an oxygen, there is a hydrogen, and there is a carbon with oxygen. So between this group and this group, the first attachment is both carbon. But the second atom, when we go, here it is hydrogen and here it is oxygen. So this gets the priority. And now if you look at the oxygen is pointing towards the observer and the hydrogen is at the bottom. So we have to simply tilt the molecule in such a way that the hydrogen goes back. So that means oxygen will be coming to this part, and we will be having the carbon with the OH here and carbon with hydrogen here. So that means priority will be like 1, 2 and 3. So this is a clockwise direction. So that is why we give this as a R isomer. And if you go to this one, we will again assign RRS for this carbon, that is the central stereogenic center. Here again oxygen is pointing towards the observer. Now the highest second priority group is on the right. So this is the one with the oxygen. This carbon is having hydrogen. So that means this will get the third number. This will get the second number. So now oxygen, this hydrogen is below. So if we just tilt it towards ourselves, what will happen is this oxygen is having priority number 1, this carbon with oxygen priority number 2, this carbon with hydrogen priority number 3. So 1, 2, 3. This is in the counterclockwise direction. So this is the S isomer. The same way you can also assign for this carbon and this carbon. So here in this particular case, pointing towards the observer is going to be the S isomer, and in this particular case pointing towards the observer is going to be R isomer. So that again we can again confirm. In this particular case the highest priority group is here on the top. Here the second one is having carbon and oxygen. Here it is carbon and hydrogen. So the second priority goes to this one, and this is the third priority one. Obviously the hydrogen is behind, so we can directly assign the number RS notation 1, 2, 3. So it is in the clockwise direction. So this is R isomer. In this particular case, 1, 2 and 3. This is in the counterclockwise direction. So this is a S isomer. So that way we can mention. And if you look at these two enantiomers, these both have 2R, 3R configuration, whereas its enantiomer has 2S, 3S configuration. So whenever we deal with enantiomers will have the RS configuration exactly opposite on all chiral centers or all stereogenic centers. So these kind of isomers are called enantiomers. We have another example given here. In this particular case, the oxygen is shown below here, and the oxygen is also shown below here. Hydrogen is pointing towards the observer. Here also hydrogen is pointing towards the observer. So these two are exact mirror images of each other, and RS nomenclature you can also assign the same way like the previous one. So here again, if you look at one center is R, the second center is S. Exact mirror image will have one center as R, another center as S. So here you don't have to be very careful, because each number, when we say 2S, it has to be 2R in the enantiomer, and the second carbon stereogenic center, which is 3R, has to be 3S. So these two, 2S becoming 2R and 3R becoming 3S, in every stereogenic center the configuration is reversed, is called the enantiomer. When we study about diastereomer, you will see why I am mentioning it here. So these two isomers are enantiomers. These are again another set of examples. And here we have shown the interconversion in a very simple way. So in the first case, what we are doing is we have 4 hydrogen. If we start from the starting compound, which has only one hydroxyl group, and the remaining things are hydrogens, we can keep on replacing 1, 2, 3, 4. All the 4 hydrogen can be replaced with hydroxyl, which leads to different types of compounds. So now we will have to see which two are enantiomers. So if we replace the H1 with OH as shown here, we get the S isomer. And if the third hydrogen is replaced, we get this particular isomer, which is RR isomer. So this is SS becoming RR. These two are enantiomers. And in this particular case, the second hydrogen, which is behind, is converted to OH. And in the same way, H4, which is behind, is converted to OH. So that means these two again are mirror images. So here it is RS and here it is SR. Actually we have to come from the reverse. So this will become S and R. So that way replacement of H2 and H4 produces another set of enantiomers. Let us look at some of the properties of enantiomers. The plus glucose is involved in the animal metabolism. Plus tartaric acid is consumed by the penicillium glucam. And adrenaline, minus adrenaline is involved in the high hormonal activity. Ephedrine is used as a drug. Asparagine and leucine were used as sweet. In other words, the particular isomer, whether it is a plus or minus, either small d or small l, is very crucial in deciding the properties of enantiomers. In the study of pharmacological substances, chiral drugs are very important because they have a very specific action, metabolism involved in our body. So here for clarity, I have not shown the hydrogen atoms. This Taxol shown here has 10 stereogenic centers, and all the stereogenic centers are represented as shown here in this particular three-dimensional structure. So why we say contrasting properties of enantiomers? Because whenever we are, this thalidomide case is a very famous example of why the R and S isomers are very crucial for the biological action. Because in earlier, in 1960s, people were not aware of the stereogenic centers importance, that is the chiral compounds importance in the drug metabolism. So they have actually made the racemic one, that is a 1:1 mixture, and then what happened was One of the isomer is actually used for treating morning sickness in the pregnant woman, but the other isomer is responsible for birth defects. So roughly 10,000 kids were born with birth defects. So that's the reason this drug was completely banned, and unfortunately later on people found out that even though the R isomer is the required one which is useful for the morning sickness, within the body it undergoes metabolism to produce the S isomer, so the thalidomide is no longer prescribed for the morning sickness in pregnant women. So that is the reason it should be very important to know the particular action of a specific enantiomer when we are giving a chiral substance as a drug. And if you look at taste, the S isomer asparagine is having a very bitter taste, whereas the R asparagine is having a very sweet taste. So it is also very essential to know which isomer to use. The same way, if you look at the smell, the S carbon is having a coriander flavor, whereas its mirror image R carbon is having a spearmint flavor. So these two are having two different smell. So in other words, each enantiomer will have a very specific function. It may be its smell, taste, or drug action. So that is the reason we have to be very careful in choosing the right enantiomer when we are using it as a drug candidate. And another important thing is the biological binding of enantiomers. The R enantiomers can exactly, in this particular example, the R enantiomer exactly fits in the binding site of the receptor for its favorable action, whereas the S enantiomer, where the two groups, that is one of the circle and the square one which I have shown here, is exactly the mirror image, so they don't fit exactly in the binding site of the receptor. In other words, only one of the enantiomer functions as the expected function, whereas the other enantiomer may have some deleterious effect. So that's the reason it should be we have to be very careful in synthesizing the drug molecules. As I mentioned earlier, enantiomers cannot be interconverted easily. In other words, this isomer and this isomer, people may very simply think that okay, just replace the OH with the hydrogen and we can simply interconvert them. But unfortunately, this isomer and this isomers, both enantiomers cannot be interconverted simply by replacing the hydrogen and oxygen. In other words, what we will be doing is we will be actually breaking the bond and adding them. So none of the enantiomers can undergo interconversion by simply rotating the bond. So here again we have the biphenyl, here we have allenes. We will be studying about the functions of the enantiomeric or the chirality which is present in biphenyls, which chirality we will be studying later. And allenes are also shown. There is no chiral center in this particular molecule, but it does show optical activity. So these are all the things we will be studying later. Let us move on to the next one, which is a diastereomer. So the major difference between enantiomer and the diastereomer is diastereomers are basically stereoisomers with a different relative configuration and are not related with object mirror image relationship. So in the case of enantiomers, they have an object mirror image relationship, but they are non-superimposable. In the case of diastereomers, they neither have non-superimposable or they are also not mirror images. So these are all the two differences between diastereomers and enantiomers. And the major difference is the different chemical and physical properties, because diastereomers are literally different compounds. They are not even like enantiomers, they are not similar in any other physical and chemical properties. Enantiomers differ only in the case of optical rotation, whereas they have same melting point, boiling point, density, and all other physical properties are same for enantiomers. Whereas in the case of diastereomers, they may have different chemical properties, they may have different physical properties. And diastereomers can easily be separated by fractional distillation or fractional crystallization or by chromatography. And if you look at the number of stereocenters, 2 to the power n, if there is n number of chiral centers, we can expect 2 to the power n stereoisomers. As I mentioned, diastereomers have no mirror image relationship and they are also non-superimposable. So here we have an example of diastereomer. So here in the first compound we have a R configuration in one of the stereogenic center and a S configuration in the other stereogenic center. But in the second compound we have the S configuration same in one of the stereogenic center, whereas one other stereogenic center has the opposite configuration. So that means SR isomer and SS isomer are basically called as diastereomers. Here is the example. So in this particular case, what we are having is the same hydroxy derivative, dihydroxy, that is pentane diol derivative we are taking as our example. So here in one case, the hydroxy group is pointing towards the observer as shown here. In the other one, it is pointing down or away from the observer. So that way, only in this particular chiral center, the configuration is changed from R to S. The other one is not at all disturbed here. So here we have the R isomer. This is also having the R isomer. So when one of the stereogenic centers configuration is retained and other one if it is changes, then those two set of compounds are called diastereomers. Here is another example. So in this particular case again, the hydroxyl is pointing downwards or pointing towards the observer. We can have two compounds which are diastereomers. So like the previous one, we can actually see here how the replacement of the groups leads to diastereomers. In the case of enantiomers, this S and S becoming R and R, these two are called the enantiomers. But these two, the first one of the carbon having the stereogenic center S, S, in the other one it becomes S and R. These two are called diastereomers. The same way here R, R becomes R, S isomers. So these two are also called as diastereomers. So in this particular slide, you will see the difference between enantiomer and diastereomer in a much simpler way. So we are taking this as our standard compound. That means this is having the RS configuration here. That is OH is pointing downwards and here the OH is pointing upwards. So this is taken as a standard and these two are generally called as enantiomers. So in other words, this carbon retains the same configuration here again. The OH is on the right hand side, here the OH is on the left hand side. So these two are enantiomers, whereas in this particular case the OH is on the central carbon, here again OH is on the central carbon, but the hydroxyl group is pointing downwards here and in this one it is pointing towards the observer. So these two are diastereomers. So in other words, to have a diastereomer, we need at least two stereogenic centers in a compound. Enantiomers can be formed even with a single chiral center, but for diastereomers to appear, we do need two stereogenic centers. And the second thing, if we are replacing one hydrogen from a particular center which is adjacent to another chiral center, or this chiral center can be in any part of the molecule, replacement of one of the hydrogen on the same carbon. If you look at here, this carbon is the same carbon. So here we are replacing hydrogen which is pointing downwards with the OH. Here we are replacing the hydrogen with the OH pointing upwards. So the carbon remains the same carbon. So if a replacement of a hydrogen on the same carbon leads to diastereomers, because we are not disturbing the chirality or the stereogenic center away from that molecule. So replacement on the same carbon gives diastereomer. Replacement on a different carbon but on the same side. If it is bottom, we have to replace another bottom hydrogen giving a enantiomer. Whereas if we replace this hydrogen and this hydrogen, we will again end up with the same enantiomer. So enantiomer relationship and the diastereomer relationship can be understood by this particular thing. For enantiomer to form, we have to replace hydrogen, different carbons. So here we are replacing one hydrogen with OH on the right hand side. In this one we are doing the same on the left hand side. So that means two carbons are different carbons. So here is another example where we can actually go through 2R, 3R and 2S, 3S are called enantiomers, whereas 2R, 3R and 2S, 3R. So 3R remains same, only 2R becomes 2S, that means these two are diastereomers. The same way here if you look at 2S and 3R, here it is 2S and 3S. So 2S remains the same, but the second carbon, that is 3R, becomes 3S. So these two are a set of diastereomers. And here we have 2S and 3S, 2R and 3S. The 3S remains the same, but the 2R changes to 2S. So these two are diastereomers. So in the case of diastereomers, at least one stereogenic center's configuration has to change. If there are more than one chiral center or the stereogenic center in the compound, for a diastereomers to have, we do need to have at least the configuration should change in one of the stereogenic center. But if you take at the enantiomers, here it is 2R, 3R becomes 2S, 3S. So all the chiral center or the stereogenic center has to have the opposite configuration. Then only they are called as enantiomers. So if you look at here, it is 2S and 3R. So the 2S should become 2R and 3R should become 3S. So both the chiral center has to invert. Then only these pairs are called as enantiomers. So this is the one thing you have to remember all the time. So for a diastereomer formation, each and every chiral center has to have the opposite configuration for the enantiomer. In the case of diastereomers, any one center can have the opposite configuration. So these, and for having a diastereomers, we do need to have minimum two chiral centers in the molecule, whereas in the case of enantiomer, we can even have enantiomers with single carbon also. So here we are just going through very quickly about some of the examples of diastereomers. So this is a S center and this is R center. And if you look at the hydroxyl is on the right here, the hydroxyl is on the left, chlorine is on the right, chlorine is on the left. So if you say in these two cases, the arrangement of groups and atoms are exactly the mirror image of each other. So that means this S will become R and the R will become S. So these two are enantiomers. And if you look at these two cases, here the hydroxyl is on the right hand side, here the hydroxyl is on the left hand side, but the chlorine is on the right hand side, chlorine is on the right hand side. So in other words, this group's arrangements and this arrangements are exactly same. So that means this is going to be the R isomer, and this one has hydroxyl on the right, this becomes hydroxyl on the left. So this will have the inverted configuration. So in other words, this is the R and this is again retained as R. So these two compounds, that is this pair, is called a diastereomers. So the same way we have a set of another enantiomer shown here. So these two, any pair from this side and this side are basically diastereomers, but the adjacent two, these two adjacent compounds, these two are enantiomers. Now let us look at how we can visualize enantiomers and diastereomers. If you look at these two compounds, you will have symmetric gloves. So in other words, whenever there is a symmetry, we do not have an optically active compound. In other words, we do not have any enantiomers or diastereomers in these kind of compounds. So if you look at this, is superimposable on the other gloves. So when you are superimposing it, so that means you are actually getting the identical compound. You are not having right and left. Even though we say this right hand and the left hand, if you exactly place it over this one, what we will end up with is exactly the symmetric gloves. That means we are not having any mirror object mirror image relationship. Since in India we play cricket a lot, I'll just take another example of the cricket gloves, and there you can actually see the difference of asymmetric gloves. So if you look at the wicket keeper gloves, you have a left hand side and this is the right hand, this is the left hand glove and this is the right hand glove. So that way what you can actually see is these two are exactly mirror image of each other. So this type of wicket keeper gloves is a good example for enantiomer. We can say this is a enantiomer because we have a object mirror image relationship between these two things. If you go to the other one, which is the batsman glove, if you look at batsman glove, is it a enantiomer or a diastereomer? If you look very carefully, you will see the difference. In the batsman glove, what you have is a padding on the thumb, which is missing on the other. This is the left hand gloves, and this is the right hand one where which is padding is present, and this is the left hand gloves which goes inside when you hold the bat. So that is the reason there is no padding on this particular thumb. So these two are not mirror images, and they are also non-superimposable on each other. So this kind of Batman gloves is basically a diastereomer. So that way you can easily remember the wicket keeper is an enantiomer, whereas the batsman is a diastereomer. So if you remember, and if you play cricket and if you are fully aware of this one, you can easily remember enantiomers and diastereomers. Here again, in a cyclic system, we are looking at the enantiomers and diastereomers. These two are exact mirror images. If I put a mirror plane in between these two compounds, this is exactly the mirror image of the other one. So these two are called enantiomers. The compound name is cis-2-methyl cyclopentanol. And I also have another compound shown here. Here again, these two are exactly the mirror image of each other. So this is also another set of enantiomer. But if I look at this top one and the bottom one, here the hydroxyl is at the top, here the hydroxyl is at the bottom, but in the second carbon the methyl group is at the top in both the cases. So that means this carbon center, that is this asymmetric center, has the same configuration, whereas this one changes its configuration. So in other words, these two are diastereomers. The same way these two, in this particular case, methyl is at the top in both the cases on the left side, and the hydroxyl is at the top, hydroxyl is at the bottom. So these two are the opposite configuration. So this compound, again, these two compounds are called as diastereomers. And this is another example. Here again, this OH is at the top, this OH is at the bottom. So if I put a mirror image, I will get the same mirror image of each other. So this is again another set of enantiomer. What about this particular case? If I put a mirror here, this is exactly the mirror image of this part. So in other words, can we say these two are enantiomers? That is a big question to answer. Unfortunately, the compound is one and the same, and it is called as a meso compound, and it is not a enantiomer, because in the case of meso compounds we will be having an internal plane of symmetry, or this part, one half of the molecule is a mirror image of the other half of the molecule. Let us look at what is the definition for meso compounds. So meso compound is one whose molecules are superimposable on their mirror image even though they contain chiral centers. So thus they are optically inactive. So here is the example of a tartaric acid. So there is a mirror image between these two. So we have 2R, 3R and 2S, 3S. So these two are enantiomers. We also have 2R, 3S and 2S, 3R. So we have another set of enantiomers. Now, if you look at the two structures on the right, they are actually identical one, because if I just rotate the molecule and I place it on this one, this becomes exactly the same molecule. So if I rotate here, I may not be in a position to exactly place the same compound. So these two are basically enantiomers, but this mirror image is having a mirror plane in between. because this part of the molecule, that is 1,2 carbon and this 3,4 carbon, these two are basically internal mirror image of the same molecule. So that is the reason this compound is an identical compound and this is a optically inactive compound. So here, as I mentioned here, even though we have two stereogenic centers, but unfortunately this molecule is optically inactive because there is an internal cancellation. So this top part of the molecule is the mirror image of the bottom part of the molecule. So that's the reason this compound is optically inactive, because the top part can be easily superimposed on the bottom part. So mesotartaric acid is one of the example which is optically inactive. In summary, let us recap what we have studied so far. We studied about various stereoisomers, that is what are configurational isomers and conformational isomers. We also studied about the conditions for optical activity, what is specific rotation. We then studied about how to assign R as nomenclature to chiral compounds or compounds having stereogenic center. We then studied about some examples of enantiomers and diastereomers, how to differentiate between enantiomers and diastereomers. We also studied about meso compounds. With this, we conclude this session. Thank you.